All right, next up we have the collision theory. So we've talked a little bit about this before. So we're going to see how collision theory relates to the rate of a reaction. And we'll look at quite a bit of things today. First says collisions must occur for a chemical reaction to proceed, but they do not indicate that the reaction will occur. So a collision between particles that does result in a chemical reaction, we call an effective collision. So we said, particles have to collide at the correct orientation. They have to collide with sufficient energy. If those two factors are met, then that collision between reacting particles will result in the formation of products. If one of those is off, particles do not collide at the correct orientation, or particles do not collide with sufficient energy, then that collision will not result in the formation of products, and we call these ineffective collisions. All right, so let's look at this here, transition state theory. So in order for a chemical reaction to occur, the reactants must collide. However, there's a momentary time where the reacting particles are stuck together and form something called a transition state or transition state complex or intermediates. There's a lot of different names for them. And so let's take a look at what that means. It says reactants pass through a short-lived high energy states before products are formed. Take a look on page 634 of your textbook. So we have reactants of I minus and CH3Cl. So hopefully you can see that there. So we have a energy diagram or heat content diagram. So in order for that reaction to occur, the particles must collide. Well, they collide and there's a brief moment in time where those particles are all stuck together. So you have iodine bonded to carbon as well as the three hydrogens and chlorine all bonded to carbon temporarily. So this is known as a transition state complex, or activated complex is another name for this. We'll see that term in just a little bit. And notice that that particle has relatively more energy than the reactants or the products. So eventually that intermediate particle breaks apart, forming our products, which are CH3I and Cl minus. Now, something to look at here, we've talked about this before as well on heat content diagrams. Activation energy, or EA, is the minimum kinetic energy that the reactant particles must possess in order to reach the transition state. So it's the energy, particles must possess a certain amount of kinetic energy in order for that collision to result in the formation of products. Or if we look at that heat content diagram, it's the energy that the reactants need to form that transition state complex. Now here it is, I mentioned this before, the short-lived molecule or particle, whatever you want to call it, in existence during the transition stage is called an intermediate or activated complex. Either one of those is fine. Take a look on page 638. We can see that as well. We have another heat content diagram. So what is different about this heat content diagram than the one on the one that we just looked at? Well, we have multiple activation energies. We have all those different bumps there. And so we'll talk about why that is a case versus the other one. So again, here our reactants are H2 and I2. Those collide to form some intermediate particles. Notice in the middle there, the middle of the graph, we have H2I. So that's formed when H2 and I collide. And so we have all these different particles involved in the reaction, though we don't show those particles in the chemical equation for a reaction. We'll see why in just a bit. All right, let's look again at some heat content diagrams. Looks a little different in my notes than in your notes, that's fine. So let's draw a couple. First one for exothermic reaction. So on the y-axis, we have enthalpy or heat content or energy or potential energy. Any of those are fine. And then, of course, on the x-axis, we have reaction progress or reaction coordinates. Your book just labels it progress of reaction. Same thing is fine. So over the course of the chemical reaction. So I've talked about it at length. Exothermic reaction, what you end up with has less energy than what you started with. So let's label all this. So this represents the energy of the reactants. Whatever this number here represents the energy of the products. And once again, the energy that you must add to the reactants is the activation energy. So from the reactants to the top of the hill is our activation energy. All right, endothermic, same axes. This time though, what you end up with has more energy than what you started with. Still have energy of the reactants there, energy of the products there, and then this time our activation energy is there. Something else I didn't label on here, but we can label it, is the delta H, the change in enthalpy or heat content during the reaction. Of course, delta H is the difference between the energy required, total energy required, and energy released, or difference in energies of the reactants and products, or all kinds of different things. So let's label it on this one. And there we have that. So I already looked at page 634. Again, it shows, take a look there. I want to show you one more thing. So this, if we read the graph from left to right, that's the heat content diagram for the forward reaction. Most chemical reactions are reversible. So in that heat content diagram, it does show the activation energy, for example, for the reverse reaction. And so just know that you can read these graphs in either direction. So say this one, for example, in the forward direction, the reaction is exothermic, but in the reverse direction, where this is actually the reactants here, this reaction is endothermic. Please keep in mind that a chemical equation does not show how a reaction occurs. A chemical equation simply shows what you start off with and what you end up with. Reaction mechanism actually shows how a chemical reaction occurs. And so we're going to see the relationship between collision theory, reaction mechanisms, and the rate law for a reaction. So it says some reactions take place in a single step, one hill on your heat content diagram. But most chemical reactions take place in a series of steps known as elementary processes. Hence, you get a heat content diagram that has multiple hills, multiple activation energy for each step in that process. This is important. The probability of having more than two particles collide. So a two-particle collision is called bimolecular. The probability of having more than two particles collide at one time is very low. Termolecular collisions, involving the collision between three particles, are extremely rare. So likely what happens during a chemical reaction is that you have the collision between two particles. Now, sometimes one particle can just break apart in a particular step, but if we have a collision between particles, more likely than not, that collision will involve only two particles. All right, so let's look at the relationship between a reaction mechanism and a rate law, or rate equations, it says here. Something important to recognize in a reaction mechanism is something called the rate determining step. The rate determining step is the step in the process that controls or governs the overall speed or rate of the reaction. The rate determining step is the slowest step in the mechanism. So a reaction is only as fast as its slowest step. And so we'll talk about how we can increase the rate of a reaction. And there's lots of ways, but ultimately it depends on the rate determining step. So let's take a look at this hypothetical mechanism. So here we have a two-step mechanism. So in the first step, we have substances C, A, and B all combine or react to form substances X and M. This is a reversible or equilibrium step. And then the second step, substance A and M react to form substances Y and C. So let's do this. Let's first start off with the overall equation for the reaction. We're going to kind of use the same thing here that we use with Hess's law, where we're going to cancel things that appear on opposite sides of our equations. So let's cross off some things. We have a C is a reactant in the first step, and it's a product in the second step. So that's going to cancel. We have M that is produced in the first step and consumed in the second step, so that's going to cancel as well. And I think everything else stays. So notice we have A's, two of them on the left side, so let's combine those. So we get 2A plus B makes X plus Y. All right, so those things we cross off, what are they? M is a reaction intermediate or activated complex. It is a product first and a reactant later. That's how we identify an intermediate. Always has to be in that order. It's produced in an early step and it's consumed in a later step, therefore never appears in the overall equation. Substance C also cancels, but it's kind of the opposite. So it starts off as a reactant. So it's a reactant first and it's a product later. So you put it in at the beginning and you get it out at the end. That sounds like the definition of a catalyst. Keep in mind that not all reactions have catalysts, but this is how we would identify a catalyst in a reaction mechanism. All right, so the experimentally determined reaction orders of reactants indicate the number of molecules of those reactants involved in 1, the slow step only if it occurs first, or 2, the slow step and any fast equilibrium steps preceding the slow step. I'll explain what I mean in just a bit. So again, what we want to look at is what's going on in the rate determining step, because we're going to use that to write our rate law. For example, if the first step is slow, then that means the rate of the reaction, again, depends on that step, and the rate of that step depends on the concentrations of these three substances. Let me say that again. If the first step is slow, the first step is our rate determining step, that means it controls the overall rate of the reaction. And the rate of that step, how fast that first step goes, depends on the concentrations of C, A, and B. So that means then our rate law looks like this. So as the number of particles of C, A, and B increase, let's say, so increasing their concentration, that's going to cause the rate to increase. There's going to be more collisions between C, A, and B if you increase the concentration of one or all three of those. Gets a little more complicated if, like in this case, the second step, let's say, is the rate determining step. So let's say the second step is slow. So first step is fast, second step is slow. So that means the rate of the second step depends on, whoops, didn't want to do that, sorry about that. The rate of the second step depends on the concentrations of A and M. We have a problem though. M is an intermediate. M's concentration depends on the concentrations of C, A, and B. How fast M is made, M is needed for the second step, but it's made in the first step. How fast M is made is determined by the concentrations of C, A, and B. So what we're going to do is we can substitute in our rate law for M. So don't write this. Actually, we can write a couple things here. So let's write the rate law for the second step. This is not the rate law for the reactions. So here I'm going to write, here, let's write it like that. rates of the second step is equal to the rate constant for the second step times, we go back to our equation here, concentration of A times concentration of M. Well, the concentration of M depends on C, A, and B. So what I'm going to do is I'm going to substitute for M into the rate law. So let's plug in C, A, and B for M. And so what we end up with then is rate equals K times concentration of C times concentration of A times A. Remember, we have this A here. And if we substitute for M, we have another A. So that's going to be A squared times concentration of B. All right, kind of already talked about it just a bit ago. In a potential energy diagram, if you have one hill, so to speak, one bump, one activation energy, that's for a one-step process, which does occur. And then if you have multiple bumps, multiple hills, that means that the reaction occurs in steps. Each step has its own activation energy. So we have different heights of our hills, so to speak, just like that heat content diagram on page 638. By the way, looking at figure 1612 and 638, what step, so this is a three-step mechanism that this reaction occurs by. Three steps because I have three activation energies. Which step is the rate determining step? Go ahead and pause the video, look at that graph and think about it. So rate determining step is the slowest step in the process, in the mechanism. Now there's a relationship between activation energy and rate. I don't know if you remember that. So the slowest step is going to be the one that has the highest activation energy. We'll see that in our next section of the notes. I just wanted to point that out here. All right, temperature effects on reaction rate and the effective activation energy on reaction rate. So EA, here we go again. Sorry, we've got a lot of repetition here. Activation energy is the energy required in a collision between reactants in order for a reaction to occur. Here's the important part. If the EA is high, then few collisions are effective, and as a result, the reaction is slow. The reaction rate is low, or the reaction is slow. Conversely, if the activation energy is low, then what's going to happen is lots of collisions will be effective. You'll have lots of effective collisions, and this is going to result in a faster reaction. All right, so let's do this. Let's take a look at, again, some heat content diagrams for both fast and slow reactions. So we'll start off with this one here. I'll let you tell me which is which. So we'll go heat content diagram for exothermic reaction. And I'm trying to show you on these two graphs that the energies of the reactants and the energies of the products are the same. So this is the same reaction, but what's different here is their activation energies. So notice on this graph, the activation energy is much lower than on this one. So which is which? Which is fast? Which is slow? So as we just read, the lower the activation energy, the faster the reaction. We'll talk later about what affects the activation energy for a reaction. Next, though, is a relationship between temperature and reaction rate. So it says, remember, in a sample, in any sample, all particles are moving at a variety of different speeds. If you increase the temperature of that substance, you will increase the average speed or velocity of all of the particles. So let's show, using this time a kinetic energy distribution curve, the relationship between um, a reaction at a higher temperature versus a reaction at a lower temperature. So we have kinetic energy on our x-axis, number of particles on the y-axis. And so we get kind of a bell-shaped curve. So let's say this is at, I don't know, 20 degrees Celsius. And let's say I'm going to arbitrarily set the activation energy there on the x-axis. So this here represents the minimum energy, minimum kinetic energy that the particles must possess in order for that collision to result in a reaction. Well, how many particles at this temperature have enough energy to react? So if we extend this up to the curve, this whole shaded area here, if we calculated the area under the curve, that would represent the total number of particles at that temperature that have enough energy to react. So let's say we take this substance and we heat it up. Well, if we increase the temperature, we're going to increase the average speed of the particles. Increasing the average speed of the particles will increase their kinetic energy. So at a higher temperature, we see something like this, where more particles have, on average, more kinetic energy. So let's say, I don't know, 50 degrees Celsius. At 50 degrees Celsius, how many particles have enough energy to react? Well, again, we're going to take our activation energy, extend it up to the curve, and shade under the red curve. What do you notice? The area under the red curve is greater than the area under the blue curve, which tells us at 50 degrees Celsius, a greater number of particles have enough energy to react. And because of that, then, the reaction will be faster at 50 degrees Celsius than at 20 degrees Celsius. So there's a diagram just like this on page 638 at the bottom of the page, figure 1613. Take a look there, but it's pretty much the same thing what I've shown here. All right, I think we're going to stop there. Next time, we'll look further at activation energy, the relationship between activation energy and the rate constant, as well as the relationship between temperature and the rate constant. All right, thanks for watching.